The conservation of energy is using less energy, let's say kilowatt hours of electricity. So we want to use less kilowatt hours of electricity, and that would save us money because we wouldn't buy the electricity then. And in doing so, we'd reduce our carbon emissions. But this requires an investment of money in dollars. And so we want to know, how much does it cost us in investment to consume less energy and emit less carbon dioxide? So this would be expressed in dollars per kilowatt hour not consumed and dollars per ton of carbon dioxide not emitted. When we look at our lighting options, we can see that an LED light uses much less electricity than an incandescent light or even a compact fluorescent light. This is the white LED light that I have in my kitchen. When it's on, it provides adequate light for the kitchen and uses much less electrical energy than the corresponding incandescent light does. It costs $10. So if we were to replace our incandescent light bulb with an LED light bulb, we would be using 53 watts less whenever it was on. This would save us money, and it would also reduce our carbon footprint. Because the LED light uses 53 watts less, we can calculate the amount of energy we save every year by taking that 53 watts and multiplying it by the amount of time we have the light running each year. However, we had to spend $10 to invest in this light bulb to begin with. So how do we calculate the cost of having saved this energy? You might just divide the two, but then you realize that an LED light lasts about 8 years if you have it running constantly. So essentially we can say this light bulb will last us a lifetime. And how we calculate these is we don't pay for this out of our pocket. We take a loan from a bank. And so if we took a loan at 7% interest rate, the capital recovery factor would be 8%. So the loan payments would be 80 cents per year. Now, so you take that 80 cents and you divide it by this amount of energy. You get 1.39 cents per kilowatt hour. This means we pay 1.39 cents for every kilowatt hour that we don't have to use. And what do we compare this cost to? Well, we should compare it to the cost of the energy that we would have used had we not made that efficiency investment, which in California would be 15 cents per kilowatt hour. So we can see that this was a very good investment. To not use the electricity, we had to spend 1.4 cents per kilowatt hour, as opposed to buying the energy for 15 cents a kilowatt hour. We remember these calculations from the financial chapter we just finished. The cost of conserved energy is just like the cost of energy of production. You take the total cost of producing it and divide it by the amount of energy. But here, rather than dividing it by the amount of energy you produce, you divide it by the amount of energy you didn't have to consume. A penny saved is a penny earned, or in this case, a kilowatt hour conserved is a kilowatt hour generated. And again, we make use of our capital recovery factor, and that's how we calculate the investment. Here's another example of spending $100 extra on a more efficient refrigerator, which saves you 250 kilowatt hours of electricity every year. And you can see in this case, the cost of conserved electricity, cost of conserved energy, is 5 cents a kilowatt hour. Again, much less than 15 cents a kilowatt hour, so we're very pleased with that investment. So here we see a graph for the United States of the cost of conserved energy calculated for a number of different technologies. One, commercial lighting, etc., air conditioning, or more efficient refrigeration. This is graphed on the y-axis. On the x-axis is the total amount of energy that could be conserved in the United States if everyone made this investment in terawatt hours per year for the country. This has been arranged from the lowest cost of conserved energy on the left to the most expensive cost of conserved energy on the right. And so you may ask yourself, how could an energy conservation measure actually have a negative cost? A commercial investment of LED lights saves money in and of itself because LED lights last almost forever. What this means is after you switch to LED lights, not only could you fire the person who's in charge of lighting because you'd never have to change them again, you'd never have to deal with costly problems that happen when lights go out. such as people falling because it's dark or getting jumped in a parking lot because it's dark. So the decision to switch to LED lights can save a company money even before they consider the cost savings in electricity use. If you were going to invest in conserved energy, you would start here with the cheapest conserved energy that would save you the most money, and move to the right and invest in more and more expensive conserved energy. And so how do you know that your investment is saving you money? Well, you compare it to the cost of using electricity, which in the United States was an average cost of 7.4 cents per kilowatt hour in 2010. The difference is the amount of money you save per kilowatt hour. And so we can look at the area under this graph and see, this is the amount of money I save per kilowatt hour. This is the amount of electricity I save in kilowatt hours. And so by multiplying them together, you would get the total cost savings for the United States if everyone made these investments. We could estimate the area of this graph and hence the potential savings for the United States in the year 2010 by estimating the average cost of conserved energy to be on the order of 2.5 cents per kilowatt hour. And so the average savings would be about 5 cents per kilowatt hour. So 5 cents a kilowatt hour times about 400 terawatt hours, and a terawatt hour is a billion kilowatt hours, yields a national savings of $20 billion. That's about $100 for every American citizen per year. Because we consumed less electricity, we also emitted less carbon dioxide, and we can calculate how much carbon dioxide we abated or how much carbon dioxide we didn't emit due to this $10 investment. We make the assumption that we produce this electricity from a single cycle natural gas facility. The carbon intensity of natural gas we know, and we divide it by the efficiency of conversion to electricity to get the carbon intensity of our electricity. And multiplying it by the amount of electricity that we didn't have to use this year, we can see that we emitted 34.5 kilograms less carbon dioxide because of the investment. So we had to pay about 80 cents per year, but from this we can subtract the electricity costs that we saved, which were the amount of electricity we didn't have to use, times the average cost of electricity in the United States, or $4.30. So the annual cost of this conservation is actually negative. We save $3.50 by not emitting this 34.5 kilograms. So the cost of abated carbon in dollars per kilogram not emitted is 10 cents, or $100 per ton of carbon dioxide not emitted, or $100 per ton of abated carbon dioxide. We can make a similar graph of costs of abated carbon dioxide as we did for cost of conserved energy. On the y-axis, we have the cost of abated carbon in dollars per ton. On the x-axis, we have the number of tons of carbon dioxide that would be abated if we took these conservation methods. We see right here for lighting systems, they calculated negative $50 per ton of carbon dioxide not emitted by using different assumptions that we used to get $100 per ton. As we go from left to right, we have less expensive ways to reduce your carbon to more expensive ways you can reduce your carbon. This study was conducted in 2007 by a powerful corporate consulting firm, McKinsey & Company, which clearly indicates the importance of this study. We can quantify the amount of carbon dioxide in the atmosphere by 2030 in parts per million if we implement increasing amount of carbon dioxide reduction measures. It's worth noting avoided deforestation, while it costs a significant amount, about $20 per ton of carbon not emitted, it results in a significant amount of reduction in carbon dioxide emissions. I've crossed out biodiesel because my interpretation of the data indicates that biofuels actually increase carbon dioxide emissions rather than decrease. This is through land use changes in digging up the soil, something we'll talk about later. Here is another graph by McKinsey & Company illustrating the same data. We can see these strategies result in reduced carbon dioxide emissions that save you money. These strategies cost you money. we can see that the areas of these two are about the same. And so as a country, the United States could reduce its carbon dioxide emissions by about 3 gigatons if it were to implement all these strategies, and it wouldn't cost anything. And so will they do it? I think the answer is certainly not. The businesses will wish to implement strategies up to this point because this will save them money, and they won't implement these because these will cost them money. The sad truth is that most of these won't be implemented anyway because, in my opinion, businesses often make long-range decisions that are not in their best financial interest. But we can take a look at some of these that, they're very simple changes. Commercial electronics, residential lightings, commercial lightings, LED, compact fluorescent. Simple changes that will save you money and reduce carbon dioxide emissions. Now you ask yourself, is 3 gigatons a lot? The United States annual emissions are about 6 gigatons of carbon dioxide per year, and so 3 gigatons represents half of our emissions. Now, these implementation strategies cost us money. If we were to implement a carbon tax of $50 per ton of carbon dioxide, the amount of money that we would have to pay to reduce our carbon dioxide emissions would be less than the amount we would have to pay in tax if we emitted the carbon dioxide. And so all of these strategies here that used to be financially unadvantageous for us now would be financially advantageous. And so what does that mean, $50 a ton of carbon dioxide emissions? We can calculate that a tax of $100 per ton of carbon dioxide emissions corresponds to approximately $1 per gallon of gas at the pump if you were to pay for your carbon emissions when you bought the fuel. In summary, you'll be expected to understand how to calculate the costs of conserved energy and the costs of abated carbon, and understand what these graphs mean. One important difference between the two is the cost of conserved electricity is almost always positive, with this one exception. But you want to compare it with the cost of buying the energy if you hadn't conserved it. And so these decisions are all financially advantageous, even though they have a positive cost of conserved energy, because you're comparing it to the cost of buying the energy. Whereas many strategies for the cost of abated carbon are negative because the money saved by reducing your energy use is included in the full cost of the decision. So these costs of conserved energy are advantageous as long as they're less than the amount you would pay for the energy. These costs are advantageous if the full cost is less than zero, is less than the carbon tax that you'd pay if you emitted that carbon dioxide.